Hello there, and welcome back to the Sleep Science. You're standing on a launch pad in the humid dark of coastal Florida, the air thick with anticipation and a faint metallic tang. Above you towers a rocket so tall it seems to poke a hole in the night. Its white body glows under floodlights, steam curling around it like a dragon trying very hard to look professional. Somewhere inside that rocket, folded with origami precision, rests the most ambitious space telescope humanity has ever built. And in just a few minutes, it's going to leave Earth without a spare parts shop anywhere nearby. No pressure. You probably won't survive this launch without ear protection, by the way. Rockets are not gentle creatures. They are controlled explosions with excellent public relations. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, tell me where you're listening from and what your local time is. There's something oddly comforting about knowing what corner of Earth you're in while we talk about leaving it behind. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The countdown reaches 0. The engines ignite. The ground trembles beneath your boots as flames bloom outward in blinding white and gold. The James Webb Space Telescope begins its ascent, riding an Ariane 5 rocket into the morning sky on December 25th, 2021, a mainstream historical fact that still feels almost poetic. Humanity's most powerful eye on the universe launched on Christmas Day, as if the cosmos itself scheduled the reveal. You watch it rise, slow at first, then faster, punching through layers of atmosphere. The roar fades into a distant thunder. In minutes, it becomes a bright dot against blue, then disappears entirely. And just like that, Webb is no longer earthbound. But here's the part that makes your palms sweat. It isn't going to low Earth orbit like Hubble did. It's heading nearly 1.5 million kilometers away to a gravitational balancing point called L2, the second Lagrange point of the Sun-Earth system. That's about 4 times farther than the Moon. If something goes wrong out there, astronauts can't just pop over with a toolkit and a can-do attitude. Webb must unfold perfectly on its own. And unfold it must. Because right now, it's packed tighter than your suitcase 5 minutes before airport security. Its 6.5-meter primary mirror, made of 18 hexagonal segments coated in gold, is folded inward. Its tennis court-sized sun shield is collapsed into layered sheets. Everything about Webb had to be engineered to fit inside the rocket fairing, then deploy autonomously in space. Engineers sometimes refer to this phase as 29 days of terror. That's not dramatic marketing. That's a professional assessment. Over 300 single-point failures were identified, components that, if they malfunctioned, could jeopardize the mission. You imagine Webb drifting through space, Earth shrinking behind it, the sun blazing ahead. Then slowly, the unfolding begins. First, the solar array swings out like a cautious wing. Then the antenna. Then the sun shield booms extend, pulling 5 delicate layers of Captain outward into their full shape. Each layer must tension correctly, spaced precisely to block and radiate away heat. Webb needs to remain extremely cold, around minus 223 degrees Celsius, for its main instruments because it observes in infrared. Any heat from itself would blind it. It's like trying to detect a candle in the distance while holding a blowtorch next to your face. Not ideal. The quirky detail? The gold coating on Webb's mirrors is only about 100 nanometers thick, roughly 1,000th the thickness of a human hair. Just enough to optimize reflection of infrared light. So yes, technically, humanity launched a gold-plated telescope into deep space. Try explaining that to a medieval king. As the days pass, the mirror segments swing into place. Motors hum softly in the vacuum. Tiny actuators adjust each hexagon with nanometer precision. Alignment is critical. If the segments don't act as one unified mirror, the images will blur. Historians still argue whether the decades-long delays and budget overruns of the James Webb Space Telescope nearly doomed it politically, or whether those same delays ensured the engineering was mature enough to succeed. Originally proposed in the 1990s, Webb's cost ballooned to nearly $10 billion. Critics questioned whether it was worth it. Supporters insisted it would transform astronomy. Now you float beside it at L2, where the gravitational pull of Earth and Sun combine in such a way that Webb can orbit the Sun in lockstep with Earth, always staying on the night side of our planet. From this vantage point, its enormous sun shield permanently blocks sunlight, Earthlight, and even moonlight. One side basks in radiation. The other remains in perpetual shadow. Slowly, patiently, the telescope cools. Instruments power on. The near-infrared camera, the mid-infrared instrument, the spectrographs all begin calibration. Tiny adjustments refine mirror alignment. The first test images come back as blurred stars scattered across the field. Engineers nudge the segments again and again until those stars converge into crisp points of light. And then, finally, Webb opens its eye. You feel the significance in your chest. This is not just another telescope. Hubble revolutionized astronomy by observing invisible and ultraviolet wavelengths from low Earth orbit, free from atmospheric distortion. But Webb peers deeper into infrared, allowing it to see through dust clouds and detect light stretched by cosmic expansion. Because the universe is expanding, a well-established cosmological fact, light from distant galaxies is redshifted into longer wavelengths. To see the earliest galaxies, you must look in infrared. Webb is designed for that task. You drift there in the cold quiet near L2, Earth a distant blue marble behind the shimmering layers of the sun shield. Everything has unfolded correctly. The mirror is aligned. The instruments are awake. Humanity has built a machine capable of looking farther back in time than ever before, and it is about to look deeper than any telescope in history. Now that Webb is fully unfolded and chilling literally to operating temperature, you begin to understand why infrared vision changes everything. If Hubble was like a pair of sharp human eyes in space, James Webb is more like heat vision layered on top of time travel. And yes, that sounds dramatic, but in cosmology, it's annoyingly accurate. You float beside the telescope at L2, its massive sun shield stretched wide like a silver kite, always facing the sun. On the cold, shadowed side, the mirrors gleam faintly gold. They are not gold for decoration. They are gold because gold reflects infrared light exceptionally well. That thin coating, only about 100 nanometers thick, is optimized specifically for wavelengths longer than what your eyes can see. Here's the crucial shift. The universe is expanding. That's not a theory in the casual sense. It's a measurement confirmed by observations since Edwin Hubble discovered in 1929 that distant galaxies are moving away from us. The farther they are, the faster they recede. This expansion stretches light itself, increasing its wavelength in a process called redshift. Imagine painting a tight zigzag on a balloon, then inflating it. The zigzag stretches. That's what happens to light traveling across cosmic distances. Ultraviolet light emitted by early stars billions of years ago arrives at Earth, stretched into infrared. If you only look in visible light, you miss the oldest chapters entirely. That's why Webb was built to see infrared. You watch as photons, some traveling for over 13 billion years, reach the mirror. They bounce from segment to segment, converge toward the secondary mirror, and funnel into the instruments. Each photon carries ancient information, like a time-stamped postcard from the early universe. Infrared has another advantage. It pierces dust. Star-forming regions are often cloaked in thick clouds of gas and dust that block visible light. Hubble's images of nebulae were stunning, but they sometimes showed only the illuminated edges of these clouds. Webb can look through them, not perfectly, but far deeper. It's like switching from headlights in fog to thermal goggles. Suddenly, the hidden shapes emerge. A mainstream fact that anchors this: infrared astronomy from Earth is limited because our atmosphere absorbs much of the infrared spectrum and emits its own heat signature. That's why Webb had to go to space and why it must remain so cold. If the telescope warmed up, its own infrared glow would swamp the faint cosmic signals it's trying to detect. Historians still argue whether placing Webb at L2 was the optimal choice compared to a more serviceable orbit closer to Earth. The advantage is thermal stability and an unobstructed view of deep space. The disadvantage is distance, no easy repair missions. The decision reflects a trade-off between ambition and accessibility. You drift closer to the instruments. The near-infrared camera, NIRCam, is Webb's primary imager for distant galaxies. It can detect wavelengths from about 0.6 to 5 microns, just beyond red visible light into deep infrared. The mid-infrared instrument, MIRI, pushes even farther, out to 28 microns, revealing cooler objects like forming planets and dusty galaxies. The precision is staggering. Webb's mirror has more than 6 times the light-collecting area of Hubble. More area means more photons captured. More photons mean deeper images. Deeper images mean fainter, more distant galaxies. You imagine the universe as an ocean at night. Hubble could see ships near the shore and faint lights offshore. Webb lowers a far more sensitive detector into the water and suddenly glimpses lanterns on the horizon, maybe even beyond the horizon. There's also spectroscopy, the real magician's trick. Instead of just taking pictures, Webb can split light into its component wavelengths, producing spectra that reveal chemical fingerprints. Dark absorption lines appear where specific molecules absorb light. That's how we identify water vapor, methane, carbon dioxide, even in the atmospheres of distant exoplanets. A quirky but true detail: when Webb observes an exoplanet transit, when a planet passes in front of its star, it measures the tiny dip in brightness and analyzes starlight filtered through the planet's atmosphere. The difference in light at specific wavelengths can reveal the presence of molecules. It's like detecting the scent of someone's perfume from across a stadium, based solely on how the air changes. Infrared also allows Webb to observe cooler objects, brown dwarfs, protoplanetary disks, even rogue planets wandering between stars. Many of these objects emit most of their energy in infrared rather than visible light. To human eyes, they'd be almost invisible. To Webb, they glow gently against the cosmic backdrop. And then there's the ultimate prize, the first galaxies. Because the farther you look, the further back in time you see. Light from a galaxy 13 billion light-years away left that galaxy 13 billion years ago. Given that the universe is about 13.8 billion years old, a widely accepted cosmological estimate based on cosmic microwave background measurements, that means Webb can peer into the first few hundred million years after the Big Bang. That era was once called the Cosmic Dark Ages. After the Big Bang's initial glow faded, before stars fully ignited, the universe was filled mostly with neutral hydrogen gas. Eventually, the first stars and galaxies formed, reionizing the universe and making it transparent to ultraviolet light. Observing this epoch requires infrared sensitivity because of extreme redshift. Historians still argue whether our theoretical models of early galaxy formation accurately predicted the speed at which structure emerged, or whether new data might force revisions. At this point in the story, you don't yet know how dramatic those revisions might be. But the stage is set. Webb is calibrated. Infrared vision is online. The telescope is cold, steady, patient. You hover beside it as it points toward a seemingly empty patch of sky, a region no larger than a grain of sand held at arm's length. And you realize something quietly thrilling. In infrared, empty rarely means empty. It means hidden. You watch as Webb fixes its golden eye on a patch of sky so small it would disappear behind a grain of rice held at arm's length. It doesn't look special, no bright nearby stars, no famous constellations, just darkness. But astronomers have learned something counterintuitive over the decades. When you stare at nothing long enough, it fills with everything. In 1995, the Hubble Space Telescope performed its famous deep field observation, a mainstream historical milestone in astronomy. It stared at a tiny, seemingly empty region for 10 consecutive days. When the image was released, thousands of distant galaxies appeared, each one a sprawling system of stars. The message was clear: the universe is crowded. Now, decades later, Webb is about to repeat that experiment, but in infrared and with far more light-gathering power. You float beside the telescope as photons stream in, some having traveled for more than 13 billion years. The detectors accumulate them patiently. Seconds turn into minutes, minutes into hours, hours into days. Webb does not blink. When the first full-resolution deep-field image is processed and released in July 2022, the reaction is immediate. Even before you analyze the science, the sheer density of galaxies hits you. Spiral galaxies, ellipticals, distorted arcs of light stretched into crescences, tiny red smudges that might be among the earliest structures ever observed. One of the first targets, SMACS 0723, is a galaxy cluster used as a gravitational lens. That's not poetic language, it's literal physics. According to Einstein's general relativity, massive objects warp spacetime. Light passing near a massive cluster bends, magnifying and distorting background galaxies. This effect allows Webb to see even farther, using gravity itself as a cosmic telescope. You notice thin, curved streaks of light around the cluster. These are distant galaxies whose images have been stretched by gravitational lensing. Without that magnification, some of them might be too faint to detect. It's like holding a magnifying glass made of dark matter and galaxies. A mainstream fact anchors this. Gravitational lensing was first confirmed observationally in 1919 during a solar eclipse, when starlight near the sun was observed to bend, matching Einstein's predictions. Over a century later, the same principle helps us peer into the infant universe. As astronomers analyze Webb's deep field, something unexpected emerges. There appear to be far more bright, massive galaxies in the early universe than standard models predicted. Now, take a slow breath with that. According to the prevailing cosmological model, lambda CDM, which includes dark energy, lambda, and cold dark matter, galaxies grow gradually. Small fluctuations in matter density after the Big Bang collapse under gravity, forming small galaxies first. Over time, these merge and accumulate mass, building larger structures. The earliest galaxies, forming within a few 100 million years, were expected to be small and faint. But Webb's deep field suggests that some galaxies within the first 300 to 500 million years after the Big Bang appear surprisingly bright and massive. Historians still argue whether these early observations represent a true challenge to the Standard Model, or whether initial mass estimates were skewed by uncertainties in redshift and stellar. Population modeling. Early data can be misleading. Brightness does not always equal mass. Star formation rates, dust content, and modeling assumptions complicate interpretation. Still, the initial shockwave is undeniable. You imagine cosmologists staring at their screens, recalculating, double-checking. The redshift measurements, how much the light has been stretched, place some galaxies at redshift 10, 12, even higher. That means their light began its journey when the universe was less than 400 million years old. And yet some appear structured, organized, not the chaotic, barely assembled blobs one might expect so soon after cosmic dawn. It's like expecting to find toddlers finger painting and instead discovering fully furnished houses. A quirky detail: some of the earliest galaxy candidates were initially nicknamed impossibly early galaxies in informal discussions. The phrase wasn't a formal classification, just a reflection of surprise. Scientists are careful with language, but humans are allowed to blink twice at unexpected data. You zoom in mentally on one faint red dot in the image. That dot might contain billions of stars. It might harbor supernovae, star clusters, perhaps even early black holes. And it existed when the universe was only a few percent of its current age. The deep field also demonstrates Webb's extraordinary sensitivity. The image captures galaxies so faint they are thousands of times dimmer than what the naked eye can see. The exposure time reveals layers upon layers of structure. The farther you look, the more red-shifted the galaxies become, their light stretched into infrared. And here's the subtle but profound part. When you look at that deep field image, you are not just seeing space. You are seeing time layered upon time. Nearby galaxies appear as they were relatively recently. Farther ones show earlier epochs. The faintest red smudges represent some of the oldest light ever detected. It's a time map disguised as a photograph. Historians still argue whether the emotional impact of the first Webb deep field rivaled Hubble's original deep field moment, or whether decades of stunning space imagery have slightly dulled public astonishment. But among scientists, the impact was sharp. Data like this reshapes grant proposals, simulation parameters, and late-night debates. You hover in the quiet near L2, the image glowing on a virtual display before you. The density of galaxies feels almost overwhelming. Every speck is a system. Every system likely contains billions of stars. Many stars may host planets, and all of it was hiding in what looked like empty space. The phrase "looking deeper than ever" suddenly feels literal. Webb didn't just capture a prettier image. It revealed that the early universe might have been busier, brighter, and more complex than many models anticipated. You stare at that grain of sand patch of sky and realize something quietly destabilizing. If this tiny sliver contains thousands of galaxies, how many more fill the rest of the sky? The darkness was never empty. It was waiting. As astronomers dig deeper into Webb's early data, the real surprise sharpens into focus. It's not just that there are many galaxies in the early universe. It's that some of them look big, too big. You lean closer to the glowing data, watching as redshift estimates place certain galaxies at less than 400 million years after the Big Bang. That's astonishingly early. Remember, the universe is about 13.8 billion years old, a figure derived from measurements of the cosmic microwave background radiation by missions like Planck. At 400 million years, the cosmos was barely 3% of its current age. In the standard lambda CDM cosmological model, structure formation is hierarchical. Small clumps of dark matter collapse first. Gas falls into those halos. Stars ignite. Over time, these small galaxies merge, forming progressively larger systems. It's a bottom-up process. Like assembling a city by first building shacks, then houses, then skyscrapers. But Webb's early observations suggest that some galaxies in this young universe may already contain billions of solar masses worth of stars. That implies extremely rapid star formation, far more efficient and accelerated than many simulations predicted. You imagine cosmologists blinking at their screens. Simulations had suggested that early galaxies would be small, irregular, and relatively faint. Instead, some appear surprisingly luminous and structured. Now, caution is critical here. Brightness does not directly equal mass. A galaxy undergoing an intense starburst, forming stars at a furious rate, can appear brighter than its true mass might suggest. Young, massive stars shine intensely in ultraviolet light, which when redshifted lands squarely in Webb's infrared sensitivity. So one possible explanation is that these galaxies are not necessarily massive in total mass, but are extraordinarily efficient star factories. Still, the pace is startling. A mainstream fact grounds the tension. Before Webb, the Hubble Space Telescope had identified galaxies up to redshift 11, corresponding to about 400 million years after the Big Bang. Webb has now pushed beyond that, identifying candidate galaxies at redshifts 12, 13, even potentially 15. Each increment slices closer to cosmic dawn. Historians still argue whether these early massive galaxy candidates genuinely overturn theoretical models, or whether improved modeling of stellar populations and dust extinction will bring observations back into alignment with predictions. The debate is active and nuanced. Some early claims of impossibly massive galaxies have already been revised downward as spectroscopic measurements refine their distances. Photometric redshifts, estimated from colors, can sometimes overestimate how far away an object truly is. Spectroscopy, which measures precise spectral lines, provides firmer confirmation. And as Webb gathers more spectroscopic data, some of the initial shock softens, but not entirely. Even after revisions, there remains evidence that star formation ramped up remarkably quickly in the early universe. Gas must have cooled and collapsed efficiently. Dark matter halos must have assembled faster than many simulations anticipated. You consider what that means. Dark matter, an invisible form of matter inferred from gravitational effects, is thought to make up about 85% of the universe's total matter content. It provides the scaffolding on which galaxies form. If early galaxies assembled faster than expected, perhaps the distribution or behavior of dark matter in the early universe was slightly different than assumed. Or perhaps the physics of gas cooling and star formation under primordial conditions was more aggressive. Early gas clouds contained almost no heavy elements, what astronomers call metals. The first generations of stars, known as population 3 stars, were likely massive and short-lived, enriching their surroundings quickly with heavier elements through supernova explosions. A quirky but fascinating possibility. If the first stars were significantly more massive than typical stars today, perhaps hundreds of times the mass of the Sun, they would have burned hot and fast, collapsing into black holes within a few million years. These early black holes could have seeded rapid galaxy growth. You imagine a newborn galaxy lighting up like a fireworks factory, stars forming in dense clusters, supernovae exploding in rapid succession, black holes gulping gas at the center. It's less a calm nursery and more a cosmic construction site running 24/7. Some researchers have even explored whether alternative cosmological models, such as modifications to dark matter properties, might better accommodate the early abundance of luminous galaxies. But such shifts are not made lightly. The Lambda CDM model has been extraordinarily successful in explaining large-scale structure, cosmic microwave background fluctuations, and galaxy clustering. Throwing it out would be like replacing the foundation of a skyscraper because a few windows didn't fit perfectly. Possible, but drastic. More likely, refinements will emerge. Star formation efficiency parameters may need adjustment. Feedback processes, how supernovae and black holes regulate further star formation, may behave differently in the primordial universe. Historians still argue whether scientific revolutions tend to occur in abrupt paradigm shifts, as philosopher Thomas Kuhn suggested, or whether they more often unfold as incremental refinements within an existing framework. Webb's early galaxy data sits delicately between those possibilities. You zoom in again on one distant, faint red smear. Its light began traveling toward us when the universe was still opaque with neutral hydrogen clouds. Somehow, within a few 100 million years of the Big Bang, matter had organized itself into a galaxy bright enough for us to detect across 13 billion years of expansion. That realization carries weight. The early universe may not have been as sluggish and chaotic as once imagined. It may have been astonishingly efficient at building structure. And if that's true, it subtly shifts your understanding of cosmic history. The story is no longer one of slow, hesitant assembly. It becomes one of rapid emergence, gravity pulling matter together with surprising urgency. You hover beside Webb, its mirrors steady, its instruments cold and precise. It continues collecting photons, adding data point after data point. Each new observation sharpens the picture, reduces uncertainties, and either reinforces or challenges existing models. The initial headlines may have proclaimed, "Webb breaks cosmology," but science is rarely that theatrical. It's more like a long chess game, moves, countermoves, adjustments. Still, you can't deny the feeling. Looking deeper than ever has revealed that the early universe might have grown up faster than expected. And that possibility alone is enough to keep cosmologists awake at night, running simulations, tweaking parameters, and quietly wondering whether the first chapters of the cosmic story need a few revisions. The ripple effect begins quietly. No alarms, no emergency meetings to rewrite physics from scratch. Just a subtle tightening of eyebrows across the cosmology community as simulation codes are reopened and parameters nudged. Because if galaxies really did assemble faster than expected, then timelines, the delicate sequence of cosmic events, may need adjusting. You hover beside Webb as it continues to gather ancient light, and you imagine cosmological models like intricate clockwork mechanisms. Each gear represents a process: dark matter collapse, gas cooling, star formation, supernova feedback, black hole growth. If one gear spins faster than predicted, the whole timing shifts. A mainstream anchor holds steady. The Big Bang model itself remains extraordinarily well supported. Observations of the cosmic microwave background radiation, first discovered accidentally in 1965 by Arno Penzias and Robert Wilson, confirmed that the early universe was hot, dense, and remarkably uniform. Tiny fluctuations in that radiation mapped the seeds of future structure. Those seeds grew into galaxies under gravity's influence. Webb does not dispute that framework. What it questions is the pace. If some galaxies at redshift 10 or higher are more luminous and potentially more massive than expected, then either star formation was more efficient, dark matter halos assembled more rapidly, or feedback mechanisms behaved differently under primordial conditions. You imagine early gas clouds composed almost entirely of hydrogen and helium. Without heavier elements to help cool the gas efficiently, models predicted that star formation might be somewhat limited, but perhaps the first stars, population 3 stars, were so massive that they rapidly enriched their surroundings with metals, accelerating subsequent star formation. There's a quirky detail about those first stars. Because they contained almost no heavy elements, they may have grown to enormous sizes, hundreds of times the mass of the Sun. Without metals to drive strong stellar winds, they could retain more mass before collapsing. And when they died, they likely did so spectacularly, either as pair instability supernovae or direct collapse black holes. If such giants were common, they would have dramatically altered their host galaxies in a short time. Historians still argue whether population 3 stars were predominantly extremely massive or whether a broader mass distribution existed. We have not observed one directly. They are inferred from theory and indirect evidence. Webb may not resolve that entirely, but its ability to detect chemical signatures in early galaxies could hint at how quickly heavy elements appeared. Then there's reionization, the epoch when ultraviolet light from the first stars and galaxies ionized neutral hydrogen, making the universe transparent to high-energy photons. Before reionization, the universe was foggy. Afterward, it cleared. The timing of this transition is constrained by cosmic microwave background measurements and quasar observations, suggesting it was largely complete by about 1 billion years after the Big Bang. If galaxies were more numerous and luminous earlier than expected, they may have contributed to reionization more efficiently. That could refine the timeline of when the cosmic fog lifted. You picture the early universe not as a dim, hesitant glow, but as a rapidly brightening web of star-forming regions, filaments of dark matter stretching across space, gas collapsing into knots, stars igniting in bursts. The first few 100 million years might have been more dynamic than many simulations suggested, but caution hums beneath the excitement. Estimating stellar mass at extreme redshifts is tricky. Astronomers rely on modeling the spectral energy distribution of galaxies, fitting observed light across multiple wavelengths to theoretical templates. Assumptions about star formation histories, dust content, and initial mass functions influence results. Small changes in those assumptions can significantly alter inferred masses. So while early Webb data hinted at galaxies too massive too soon, subsequent refinements have moderated some of those claims. Not erased them, just sharpened them. The tension remains, but it is more nuanced than the first wave of headlines implied. You think about how science absorbs surprises. Rarely does one dataset topple a paradigm. Instead, anomalies accumulate. Patterns emerge. Over time, the weight either forces revision or reveals hidden assumptions that can be adjusted. Historians still argue whether the greatest scientific revolutions, like the shift from Newtonian gravity to Einstein's relativity, were inevitable given accumulating anomalies, or whether they required singular conceptual leaps. Webb's findings, for now, seem to belong to the incremental camp. But incremental does not mean insignificant. If star formation efficiency in the early universe needs upward revision, that influences how we interpret galaxy growth across cosmic time. It affects predictions for how many faint galaxies should exist just beyond current detection limits. It informs future surveys, future telescope designs. You glance at Webb's steady silhouette against the blackness. It is not reacting emotionally to its discoveries, it simply measures, photon by photon, spectrum by spectrum, and each measurement narrows uncertainty. There's also a philosophical shift unfolding. For decades, the early universe was often described as simple, smooth, homogeneous, gradually evolving into complexity. But Webb's deep observations hint that complexity may have emerged with surprising speed. Structure may have blossomed rapidly from those tiny fluctuations in the cosmic microwave background. You consider the analogy of frost forming on a window. At first glance, the glass seems uniform. Then, suddenly, delicate crystalline patterns spread quickly, branching outward in intricate webs. The underlying physics was always there. The pattern simply needed the right conditions. Perhaps the early universe was similar. Once gravity gained the slightest advantage, structure propagated efficiently. Historians still argue whether our intuition about slow cosmic evolution was influenced by the limitations of earlier instruments. When you can only see faint smudges at extreme distances, you assume simplicity. Now that you can resolve more detail, the narrative gains texture. Webb does not declare that everything we knew was wrong. It whispers that the opening chapters may have been busier than we thought, and that whisper matters. Because if galaxies assembled faster, if stars ignited earlier, if black holes grew rapidly from the beginning, then the universe matured quickly, not instantly, but briskly. You float beside the telescope as it slews gently toward another distant target. It does not care about debates. It cares about alignment, calibration, exposure time. But you care, because every refinement in the cosmic timeline reshapes how you understand your own place in it. Looking deeper has not shattered the story. It has accelerated it. Now you let your gaze drift away from the edge of the observable universe and back towards something closer, though closer in astronomy still means hundreds or thousands of light years away. Because while Webb stunned everyone with ancient galaxies, it also turned its infrared eye towards stellar nurseries. And this is where the magic becomes almost unfairly beautiful. You float beside the telescope as it pivots toward a dense, dusty region inside the Carina Nebula, about 7,600 light-years from Earth. A well-studied star-forming region, first imaged spectacularly by Hubble. In visible light, Carina looks like towering cliffs of gas and dust, illuminated at the edges by young hot stars. But much of its interior remains opaque. Dust blocks visible wavelengths efficiently. Infrared, however, slips through. Webb's image of the cosmic cliffs reveals something astonishing. What looked like a solid wall of gas is actually riddled with cavities, jets, and embryonic stars. Hundreds, possibly thousands, of protostars glow faintly within the cloud, each surrounded by swirling disks of material that may one day form planets. A mainstream fact anchors this scene. Stars form when dense regions within molecular clouds collapse under gravity. As the gas contracts, it heats up, forming a protostar. Surrounding material flattens into a rotating protoplanetary disk. Over time, nuclear fusion ignites in the core, and a new star is born. This process has been studied for decades, but Webb reveals it in unprecedented detail. You notice thin, bright streaks shooting outward from some protostars. These are bipolar jets, streams of gas launched along magnetic field lines as material spirals inward. They punch through the surrounding cloud, carving tunnels and creating shock fronts that glow in infrared. It's not a quiet nursery. It's a construction site with cosmic blowtorches. A quirky detail: some of these protostellar jets extend for light years. That means a newborn star, barely ignited, can influence a region of space vast beyond everyday comprehension. Talk about making an entrance. Webb's infrared sensitivity also reveals brown dwarfs, objects too small to sustain hydrogen fusion in their cores. They're often called failed stars, which feels a bit harsh. They still glow faintly from residual heat, especially in infrared. Hubble could spot some, but Webb sees many more. You imagine drifting through one of these dusty clouds. To human eyes, it would be pitch black. To Webb, it's a landscape alive with faint embers. Historians still argue whether star formation efficiency within molecular clouds is primarily regulated by turbulence and magnetic fields or by feedback from newly formed stars, jets, radiation, pressure, and stellar winds. Webb's detailed observations of these regions may help refine that debate by revealing how common and powerful these feedback mechanisms truly are. You zoom in on a protoplanetary disk, sometimes called a proplyid. Within that flattened swirl of gas and dust, microscopic grains collide and stick together, forming pebbles, then planetesimals, then if conditions are right, planets. Our own solar system formed from such a disk about 4.6 billion years ago, a date confirmed by radiometric dating of meteorites. That's a cornerstone of planetary science. Now Webb is watching similar processes unfold elsewhere. In some images, you can even detect chemical signatures within these disks: water vapor, carbon-bearing molecules. The building blocks of planets and potentially life are present from the beginning. And here's where the story subtly connects back to those early galaxies. The first generations of stars enriched the universe with heavy elements, carbon, oxygen, silicon, through supernova explosions. Without those elements, dust grains and rocky planets could not form. The rapid star formation hinted at in the early universe may have seeded later stellar nurseries with the ingredients needed for complex chemistry. You feel the continuity. From the first massive stars to these gentle protostars forming in dusty clouds, there is a chain of enrichment and renewal. Webb's images of the Pillars of Creation, a region in the Eagle Nebula famously photographed by Hubble in 1995, drive this home. In visible light, the pillars look like solid columns. In infrared, they become semi-transparent, revealing newborn stars hidden inside. It's like turning on a light inside a cave you thought was empty. There's something almost mischievous about infrared astronomy. It exposes secrets dust tried to hide. Historians still argue whether our long-standing models of star formation timescales accurately capture the complexity observed in real molecular clouds. Some simulations predict orderly collapse, others reveal chaotic, filamentary fragmentation. Webb's high-resolution infrared data adds fresh constraints to those models. You drift among the glowing clouds in your mind. Each tiny point of light represents a potential solar system. Some may host gas giants, some rocky planets, some may remain barren. But statistically, given the sheer number of stars forming across the galaxy, the odds feel expansive. And here's a humbling thought. The same physics governing these distant nurseries govern the formation of our sun. Gravity, angular momentum, thermodynamics, unchanged across billions of years and thousands of light years. Webb has not only looked deeper into space, it has looked deeper into origins. You watch as dust glows softly in mid-infrared wavelengths, revealing cooler regions invisible to visible light telescopes. You see cavities carved by stellar winds, illuminated rims where radiation sculpts gas into intricate shapes. The universe does not form stars quietly, it sculpts them from turbulence and light. And by seeing through dust, Webb reveals that what once seemed like static, opaque walls are actually dynamic, evolving ecosystems. From ancient galaxies assembling faster than expected to newborn stars igniting in hidden clouds, the message begins to coalesce. The universe may be more efficient, more dynamic, more industrious than we once assumed. Not chaotic beyond comprehension, but busy, very, very busy. Now you let Webb aim even farther back, past dusty nurseries, past mature galaxies, past familiar structure toward the faintest, reddest smudges imaginable, toward the oldest starlight ever seen. You float beside the telescope as it locks onto another deep field, integrating light for hours upon hours. Each photon that lands on the mirror has traveled nearly the entire age of the universe. Some began their journey when the cosmos was less than 300 million years old. Pause there. The universe today is about 13.8 billion years old, a figure derived from measurements of the cosmic microwave background and the expansion rate of space. At 300 million years after the Big Bang, there were no spiral galaxies like the Milky Way, no heavy elements beyond those forged in the very first stars, no planets as we know them, just nascent structure emerging from primordial darkness. This era is often associated with the end of the so-called cosmic dark ages. After the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen, a period called recombination around 380,000 years after the beginning. The cosmic microwave background radiation comes from that time. Afterward, the universe entered a long stretch where no stars yet shone. Eventually, gravity pulled matter into dense pockets, igniting the first stars and galaxies. Webb is peering directly into that transition. You imagine one of those earliest galaxies, small, irregular, fiercely bright in ultraviolet light. That ultraviolet radiation has been stretched by cosmic expansion into infrared by the time it reaches us. Without Webb's infrared sensitivity, it would remain invisible. Spectroscopic measurements confirm redshifts beyond 12 for some objects, meaning we are seeing them as they were roughly 350 million years after the Big Bang. These are not guesses based solely on color. Webb's spectrographs detect specific emission lines, like hydrogen's Lyman alpha line, shifted into infrared, providing firmer distance estimates. That's a mainstream milestone. For the first time, humanity has spectroscopically confirmed galaxies from such an early epoch. You feel the scale of it. These photons left their source before Earth existed, before the sun formed, before even our galaxy had fully assembled. They traveled unimpeded through expanding space for over 13 billion years, only to end their journey on a gold-coated mirror drifting at L2. There's something almost reverent about that. Historians still argue whether the first generation of stars, population 3, were exclusively massive and short-lived, or whether smaller stars also formed among them. We have not yet directly observed a pure population 3 star. They are thought to have died quickly, enriching their surroundings with heavier elements. Webb may not see them individually, but it can observe galaxies so early that they are likely dominated by such primordial stars. You imagine those first stars blazing intensely, emitting ultraviolet radiation that ionized surrounding hydrogen gas. This reionization gradually transformed the universe from opaque to transparent at high energies. Webb's observations of early galaxies help map when and how that transition occurred. One particularly distant galaxy candidate, observed by Webb, was initially estimated at a redshift around 16, placing it roughly 250 million years after the Big Bang. Subsequent analyses refined that value, but the mere possibility highlights how close we are pushing to cosmic dawn. And here's the subtle shift. Before Webb, our observational window into this era was narrow and uncertain. Now it is widening. Each confirmed high redshift galaxy adds a data point to the timeline of early structure formation. You drift closer to the data stream. The faintness of these galaxies is extreme. They are tiny smudges even in Webb's deep exposures. Yet they are not singular stars. They are collections of millions or billions of stars bound together by dark matter halos. That realization reshapes your intuition. Even at 300 million years, the universe had already assembled star systems in organized structures. Gravity wasted no time. A quirky thought slips in. If you could stand on a hypothetical planet orbiting a star in one of those early galaxies, the night sky would look dramatically different. Fewer mature galaxies in the distance, more intense ultraviolet radiation, a cosmos still in the process of lighting up, not peaceful, not settled. Historians still argue whether our human tendency to imagine the early universe as simple and featureless stems from psychological bias, assuming beginnings must be crude. But physics does not respect narrative simplicity. Given slight density fluctuations, gravity amplifies them relentlessly. Structure emerges quickly once conditions allow. You consider the cosmic microwave background map, the faint temperature fluctuations measured by satellites like COBE, WMAP, and Planck. Those tiny variations, only 1 part in 100,000, seeded everything. From that subtle imprint, galaxies formed. Webb is now observing the outcome of those fluctuations only a few 100 million years later. It's like seeing the first green shoots sprouting from seeds you once saw scattered on barren ground. And the shoots are more vigorous than expected. You hover in the quiet near L2 as Webb continues its patient survey. The telescope is not emotional. It does not gasp at the sight of ancient galaxies. It measures, it calibrates, it confirms, but you can feel the shift. The phrase "oldest starlight ever seen" is not hyperbole. It is a literal boundary being pushed outward. Each new high redshift confirmation edges us closer to the moment when the first stars ignited. We are approaching the cosmic sunrise. And with each deeper exposure, the darkness yields more structure than anticipated. Looking deeper has not revealed emptiness. It has revealed that the universe wasted very little time becoming luminous. Now your attention shifts from starlight to something even more gravitationally dramatic. Because if galaxies were assembling quickly in the early universe, then something else must have been growing quickly too. Black holes. You hover beside Webb as it collects spectra from a compact, distant galaxy whose light has traveled more than 13 billion years to reach us. At its center, the spectral lines appear broadened, stretched in a way that suggests gas is moving at enormous speeds. That's often a telltale signature of material swirling around a supermassive black hole. And here's where things get interesting. Supermassive black holes, millions to billions of times the mass of the Sun, are thought to reside at the centers of most large galaxies. The one at the center of our Milky Way, Sagittarius A, has a mass of about 4 million suns. That's a mainstream measurement confirmed by tracking the orbits of stars near the galactic core. But in the early universe, how did such massive black holes form so quickly? Standard models suggest that black holes begin as remnants of massive stars, perhaps tens or hundreds of solar masses, then grow by accreting gas and merging with other black holes. However, there's a theoretical limit to how fast they can grow, known as the Eddington limit. If they accrete too rapidly, radiation pressure from infalling material pushes gas away, throttling further growth. And yet, even before Webb, astronomers had detected quasars, extremely luminous galactic nuclei powered by accreting supermassive black holes, at redshifts greater than 7. That means billion solar mass black holes existed less than 800 million years after the Big Bang. Webb is now extending that frontier, identifying candidate active galactic nuclei even earlier. Some early galaxies appear to host black holes that are surprisingly massive relative to their host galaxies. You imagine a young galaxy barely assembled, yet already harboring a central black hole gulping gas like it's in a cosmic eating contest. Historians still argue whether these early black holes formed from light seeds, the remnants of population 3 stars, or from heavy seeds, created by the direct collapse of massive gas clouds into black holes without first forming stars. The heavy seed scenario could produce black holes of 10,000 to 100,000 solar masses right from the start, giving them a head start in the growth race. Webb's ability to detect faint, distant active galactic nuclei provides new clues. By analyzing emission lines and infrared luminosity, astronomers can estimate black hole masses and accretion rates. Some results suggest that black hole growth in the early universe may have been more efficient or less regulated than in later epochs. That raises fascinating possibilities. Perhaps early galaxies were denser, funneling gas more effectively toward their centers. Perhaps feedback mechanisms, jets and radiation from accreting black holes, had not yet stabilized into the self-regulating cycles observed in mature galaxies today. A quirky detail, some early black holes may have grown so rapidly that they outpaced the growth of their host galaxies, temporarily becoming proportionally more massive than typical modern galaxy-black hole ratios. In today's universe, there's a fairly tight correlation between the mass of a galaxy's central black hole and the mass of its bulge. But Webb hints that this relationship may not have been so tidy in the beginning. You imagine the early cosmos not just as a nursery of stars, but as a workshop of gravity wells, dense pockets where matter cascades inward, releasing torrents of energy. And remember, quasars are among the brightest objects in the universe. A single active galactic nucleus can outshine its entire host galaxy. That means some of the earliest luminous beacons in the cosmos may have been powered not just by stars, but by black holes. There's something poetically dramatic about that. The universe's first light may have been fueled by its darkest objects. Historians still argue whether supermassive black holes drive galaxy formation or merely grow alongside it. It's a chicken and egg question on a cosmic scale. Does the black hole regulate star formation through energetic feedback, or does galaxy growth determine black hole feeding rates? Webb's observations of early systems, where the balance may not yet be established, could help clarify that dynamic. You zoom in mentally on a distant, faint speck. Within it, gas spirals into a central abyss, heating to millions of degrees, emitting intense radiation. That radiation escapes, stretched by cosmic expansion into infrared, where Webb detects it. Without infrared sensitivity, much of that activity would remain hidden. Dust obscures active nuclei in visible light. Infrared penetrates the shroud, revealing the energetic core. And here's the subtle implication. If black holes were growing rapidly in the first few 100 million years, they may have played a significant role in reionization. High-energy radiation from accreting black holes could have contributed to ionizing the intergalactic medium alongside early stars. That possibility shifts the narrative slightly. The end of the cosmic dark ages may not have been solely a story of starlight. It may also have been shaped by the glow of matter falling into black holes. You float in the cold shadow of Webb's sunshield, watching data stream in from galaxies whose central engines formed almost at the dawn of time. The universe, it seems, did not wait politely for structure to settle before lighting up its most extreme phenomena. Galaxies formed quickly, stars ignited fiercely, Black holes grew hungrily. Looking deeper has revealed not a timid early cosmos, but an energetic one, dense, dynamic, and perhaps more chaotic than our simplified models once suggested. And if the darkest objects were already so powerful so early, then the story of cosmic evolution becomes even more intertwined, gravity, light, and shadow shaping one another from the very beginning. Webb continues to stare into that ancient era, quietly collecting evidence, and the more it sees, the clearer it becomes that the first chapters of the universe were anything but dull. Now you begin to notice something subtle but transformative about Webb's power. It's not just showing you where galaxies and black holes are, it's telling you what they're made of. You drift beside the telescope as it switches from imaging mode to spectroscopy. Instead of producing a beautiful, layered photograph, it stretches incoming light into a barcode of wavelengths. Across that spectrum, dark absorption lines and bright emission lines appear, each one corresponding to a specific element or molecule. It's like reading the universe's ingredient list. A mainstream cornerstone of astronomy anchors this. Spectroscopy has been used for over a century to determine stellar composition. In the 1860s, scientists realized that each chemical element produces unique spectral lines. That's how helium was first identified in the sun's spectrum before it was discovered on Earth. The method is old, the sensitivity is new. Webb's infrared spectrographs now extend that technique to galaxies forming just a few 100 million years after the Big Bang. And here's what's remarkable. Even at those early epochs, Webb detects signatures of heavy elements: carbon, oxygen, neon. That means the first generations of stars must have already lived and died, enriching their surroundings through supernova explosions. The early universe began with mostly hydrogen and helium, forged in the first few minutes after the Big Bang. Heavier elements, what astronomers collectively call metals, were produced later inside stars. So when Webb detects oxygen emission lines in a galaxy at redshift 10 or beyond, it's seeing evidence of stellar evolution already well underway. You imagine those first massive stars burning furiously, fusing hydrogen into helium, then into heavier elements, before exploding and seeding space with enriched gas. That enriched gas collapses again, forming new stars and eventually planets. The cycle begins astonishingly early. Historians still argue whether metal enrichment in the early universe proceeded uniformly across regions or whether it was patchy, some galaxies rapidly enriched, others remaining pristine longer. Webb's ability to measure metallicity in distant galaxies may help resolve that debate. You zoom in on a distant galaxy's spectrum. Bright emission lines from ionized oxygen suggest active star formation. The intensity ratios between different lines allow astronomers to estimate temperature, density, and chemical abundance. It's not just there is oxygen. It's there is this much oxygen under these physical conditions. That level of detail from billions of light years away feels almost unfair. A quirky but true detail. Some early galaxies appear to have surprisingly low dust content compared to later galaxies. Dust forms from heavier elements, so its presence is tied to previous generations of stars. Measuring dust extinction in these early systems helps refine models of how quickly the first supernovae enrich their surroundings. And then there's nitrogen, carbon, silicon. Each detection pushes back the timeline of when complex chemistry emerged. You start to sense the broader implication. If heavy elements were already widespread within a few 100 million years, then the raw materials for rocky planets may have been available earlier than once thought. Now, that doesn't mean habitable planets were common immediately after the Big Bang. Conditions were still extreme, radiation levels were high, galaxy mergers frequent, but chemically speaking, the universe did not wait long to diversify beyond hydrogen and helium. Historians still argue whether the first potentially habitable environments could have existed much earlier than previously assumed, or whether intense early cosmic radiation would have sterilized. Nascent planetary systems. It's a delicate balance between enrichment and stability. Webb's chemical fingerprints extend beyond galaxies. It also examines interstellar gas clouds, protoplanetary disks, and even exoplanet atmospheres. The same spectral principles apply everywhere. You imagine looking at a faint galaxy 13 billion light-years away and determining not only its distance but its elemental composition. It's like tasting a drop of water from an ocean across time. And this is where the phrase "changes everything" begins to feel less dramatic and more literal. Because once you can measure chemical composition across cosmic history, you can trace the evolution of matter itself, from primordial hydrogen to oxygen-rich star-forming regions, from pristine gas to dusty galaxies, from the first supernovae to complex molecular clouds. The universe is not just expanding, it's chemically maturing. A mainstream fact grounds this transformation. The abundance of heavy elements in galaxies generally increases over time as successive generations of stars process and redistribute material. Webb allows astronomers to measure this enrichment at earlier epochs than ever before. You watch as a distant galaxy's spectrum flickers on your imagined display. Oxygen lines glow. Hydrogen recombination lines mark star-forming regions. The redshift stretches everything toward longer wavelengths. Light that began as ultraviolet now whispers in infrared. Historians still argue whether the overall chemical evolution of the universe follows a smooth, predictable curve, or whether bursts of intense star formation caused episodic jumps in metallicity. Webb's data will refine that curve. You feel the story layering together. Early galaxies formed faster than expected. Black holes grew rapidly. Heavy elements appeared quickly. The early universe was not a chemically primitive wasteland for long. It was a forge, operating at remarkable speed. And by reading those spectral fingerprints, Webb has turned faint smudges of light into detailed chemical profiles. Looking deeper did not just show more objects. It revealed what those objects are made of, and once you know what something is made of, the story becomes tangible. Stars are not abstract points of light. They are factories of carbon and oxygen. Galaxies are not just shapes. They are ecosystems of evolving chemistry, and the earliest chapters of that evolution are now visible, written in infrared barcodes across billions of years. You hover in the quiet, golden mirror, reflecting ancient photons. The universe has always been speaking in spectra. Webb simply learned how to listen better. Now you pivot from galaxies and ancient chemistry to something much closer, though still impossibly far by everyday standards. Because while Webb has been rewriting cosmic history, it has also been quietly dissecting the atmospheres of alien worlds. You hover beside the telescope as it locks onto a star hundreds of light years away. The star itself looks unremarkable, just another point in the vast grid of the sky. But orbiting it is a planet, and that planet is about to pass directly in front of the star from Webb's point of view. This is called a transit. As the planet crosses the stellar disk, a tiny fraction of starlight filters through its atmosphere before reaching Webb's mirror. That light carries chemical fingerprints. Spectroscopy again becomes the magician's trick. A mainstream fact anchors this method. The transit technique has been used for years by missions like Kepler and TESS to discover thousands of exoplanets by measuring slight dips in starlight. Webb extends this technique by analyzing the starlight spectrum during transit to identify atmospheric molecules. The first exoplanet atmosphere Webb analyzed in detail was WASP 96b, a hot gas giant roughly 1,150 light-years away. When Webb released its transmission spectrum, it clearly showed the signature of water vapor, distinct absorption features across infrared wavelengths. That was not the first detection of water in an exoplanet atmosphere, but it was the most detailed infrared spectrum ever obtained for such a world. You imagine the starlight passing through that distant planet's atmosphere, some wavelengths absorbed by water molecules, others passing through unimpeded. Webb captures the pattern, turning it into a graph that reveals invisible chemistry. It's like detecting the flavor of soup from the steam rising off it. And Webb doesn't stop at hot gas giants. It turns its attention to smaller, potentially rocky worlds. One of the most intriguing systems is TRAPPIST-1, located about 40 light-years away, a relatively close neighbor in cosmic terms. It hosts 7 Earth-sized planets, several within the star's habitable zone. Webb's observations of TRAPPIST-1b and c suggest that at least some of these planets may lack thick, hydrogen-dominated atmospheres. That's significant because it narrows down what kinds of atmospheres they might possess. Historians still argue whether M-dwarf stars like TRAPPIST-1 can support long-term habitable planets given their frequent flares and high-energy radiation output. Webb's atmospheric measurements help address that debate by searching for evidence of atmospheric retention or erosion. Then there's the exoplanet K2-18b, a world about 120 light-years away. Webb detected carbon dioxide and methane in its atmosphere, along with hints of dimethyl sulfide, a molecule associated on Earth with biological processes. Now, pause. This is where headlines can outrun caution. Dimethyl sulfide detection is tentative and requires further confirmation. It is not proof of life. It is a possible biosignature candidate. Scientists are careful here. Extraordinary claims require extraordinary evidence. But the mere fact that we can detect complex carbon-bearing molecules in the atmosphere of a distant exoplanet marks a profound leap in capability. You imagine analyzing the spectrum, dips at wavelengths corresponding to methane, carbon dioxide, perhaps water vapor. The ratios between these gases matter. On Earth, the coexistence of oxygen and methane in large quantities is considered a potential biosignature because they react and would not persist together without continuous replenishment. Webb is not yet detecting oxygen in rocky exoplanet atmospheres at Earth-like levels. That remains extremely challenging, but it is laying the groundwork. A quirky detail: some exoplanet atmospheres appear surprisingly puffy, extended, hazy envelopes of gas that scatter light. Webb's infrared precision allows scientists to detect high-altitude clouds and hazes, which can obscure deeper atmospheric layers. Even that absence of a clear signal tells a story. And here's the quiet shift in perspective. Before Webb, exoplanet atmospheres were largely inferred from limited data points. Now, we are entering an era of comparative exoplanetology, studying multiple worlds in detail, comparing atmospheric compositions, temperatures, and chemical processes. You imagine future textbooks listing categories: hydrogen-rich mini-Neptunes, water-rich sub-Neptunes, super-Earths with thick carbon dioxide atmospheres. Webb is populating those categories with real data. Historians still argue whether the first definitive detection of a biosignature on an exoplanet will occur in this decade or require future, even more sensitive telescopes. Webb may not deliver the final answer, but it is building the foundation. You drift back slightly, taking in the broader picture. Webb looked deeper into cosmic time and found galaxies forming faster than expected. It looked into stellar nurseries and saw hidden stars. It analyzed early chemical enrichment, and now it's dissecting the atmospheres of distant planets, searching for molecules associated with life. Looking deeper did not just change cosmology. It brought the search for life beyond Earth into sharper focus. Each exoplanet spectrum is a whisper from another world. Most whisper of heat, gas, and chemistry. None yet whisper unequivocally of life, but the language is becoming clearer. You imagine the faint transit signal repeating again and again as the planet orbits its star. Webb watches patiently, stacking observations to reduce noise. Precision improves, confidence grows. The universe is no longer just a backdrop of galaxies, it is a landscape of atmospheres. And somewhere among those atmospheres, chemistry might be doing something interesting. Webb cannot smell alien oceans or hear distant winds, but it can measure absorption lines to astonishing precision. And that precision is narrowing the gap between speculation and evidence. Looking deeper has not yet found life, but it has made the search scientifically rigorous in a way that was barely imaginable a generation ago. And that quietly changes everything. Now you linger on those atmospheric spectra a little longer, because this is where molecules begin to feel almost personal. Water, methane, carbon dioxide. Words that belong not only to astronomy, but to weather reports and climate models and the air you're breathing right now. You float beside Webb as it studies another exoplanet transit. The star dims by a fraction of a percent. The data stream looks unimpressive at first, just tiny variations in brightness across wavelengths. But when the light is separated into its infrared spectrum, patterns emerge. Distinct absorption features appear at wavelengths where water vapor absorbs strongly. Another dip corresponds to carbon dioxide. A subtle curve suggests methane. These are not artistic impressions. They are statistical signatures rising above instrumental noise. A mainstream scientific anchor. Water vapor, carbon dioxide, and methane have all now been detected in multiple exoplanet atmospheres using Webb's infrared spectroscopy. In particular, the detection of carbon dioxide in WASP-39b was a milestone, confirming Webb's sensitivity to molecules critical for understanding planetary formation and atmospheric chemistry. You imagine the atmosphere of a hot gas giant shimmering in the light of its star. Temperatures of over 1,000 degrees Celsius. Clouds made not of water droplets but of silicate particles, essentially sand clouds. Yes, that's real. Some hot exoplanets likely host clouds composed of vaporized rock that later condenses into tiny grains. Weather reports would be abrasive. Historians still argue whether gas giants migrate inward after formation or form close to their stars in situ. Atmospheric composition, particularly the ratios of carbon to oxygen, can hint at where in the protoplanetary disk the planet originally formed. Webb's measurements are beginning to refine those formation models, but your attention shifts to smaller worlds. Sub-Neptunes, super-Earths, planets between Earth and Neptune in size, which curiously do not exist in our own solar system. Kepler revealed that such planets are common in the galaxy. Webb is now probing their atmospheres. One example is GJ 1214b, a super-Earth with a thick, hazy atmosphere. Earlier observations struggled to determine whether it was water-rich or hydrogen-dominated because clouds obscured spectral features. Webb's broader infrared coverage helps break that degeneracy, offering clearer insight into its atmospheric structure. You imagine layers of atmosphere stacked like invisible blankets: hydrogen, helium, water vapor, perhaps ammonia. Each layer absorbs light differently. By modeling the depth and shape of spectral lines, astronomers infer temperature profiles and molecular abundances. It's atmospheric forensics conducted across light years. Now comes the delicate part: biosignatures. On Earth, life has dramatically altered the atmosphere. Oxygen, making up about 21% of our air, is largely the result of photosynthetic organisms. Methane, though present in small quantities, is constantly replenished by biological and geological processes. The coexistence of oxygen and methane in disequilibrium is considered a strong biosignature candidate. Webb, however, is not yet optimized to detect Earth-like oxygen levels on true Earth analogs orbiting Sun-like stars. That remains beyond its primary design capabilities. But it can detect carbon dioxide, methane, and water vapor in certain favorable systems, especially around smaller, cooler stars where transit signals are stronger. When hints of dimethyl sulfide appeared in early data for K218b, excitement rippled outward. On Earth, dimethyl sulfide is produced primarily by marine phytoplankton. But historians still argue whether such molecules can be generated abiotically under certain planetary conditions. Chemistry is versatile. Life is not the only path to complexity. And so caution remains the rule. You imagine the scientific process unfolding, independent teams reanalyzing the same data, refining models, checking for instrumental artifacts. Claims are tested, confidence intervals are recalculated. It's slow, meticulous, almost stubbornly conservative. But that caution is strength, not weakness. Because when a detection eventually rises above all doubt, if it does, it will rest on layers of scrutiny. A quirky but fascinating fact: Webb's instruments must account for minute thermal variations within the telescope itself. Even slight changes in temperature can influence infrared measurements. Engineers model these effects carefully to avoid mistaking instrument noise for planetary chemistry. It's like tuning a piano in a room where the temperature changes by a fraction of a degree and somehow expecting perfect pitch. You drift outward, seeing Webb not just as a telescope but as a chemical detective. It cannot sample atmospheres directly. It cannot scoop alien air into a vial. But it can decode the fingerprints left in starlight. And with each detection of water, methane, or carbon dioxide, the statistical landscape shifts. We now know that water vapor is common in giant planet atmospheres. Carbon-bearing molecules are widespread. Cloud layers are complex. Atmospheric chemistry varies dramatically from world to world. The universe is not chemically uniform. It is exuberantly diverse. Historians still argue whether life requires a narrow set of atmospheric conditions or whether it could thrive under chemistries radically different from Earth's. Webb's growing catalog of exoplanet atmospheres expands the parameter space for that debate. You picture a distant ocean world under a red dwarf star, its sky tinted copper by thick haze, or a rocky planet with carbon dioxide clouds drifting over volcanic plains, or a water-rich sub-Neptune with a deep global ocean beneath a hydrogen envelope. These are no longer pure speculation. They are emerging as measurable possibilities. Looking deeper did not just reveal ancient galaxies. It revealed that atmospheres, those fragile, shimmering shells around planets, are detectable across interstellar space. And once you can measure atmospheres, you can ask the next question with scientific seriousness. Is any of that chemistry alive? Webb has not answered that yet. But it has transformed the question from philosophy into observation. You hover beside the golden mirror, feeling the quiet weight of that shift. The search for life is no longer limited to radio signals or speculative probes. It is embedded in spectral lines, in absorption features, in tiny dips of starlight. And every new dataset sharpens the picture. The molecules are there, the diversity is real, the possibilities are widening. Now your gaze drifts back outward, from planets and molecules to the grand scaffolding that holds galaxies together. Because as Webb peers deeper into the early universe and catalogs galaxies that seem brighter, denser, and perhaps more mature than expected, an old, invisible question resurfaces. Dark matter. You float beside the telescope as it observes a massive galaxy cluster acting as a gravitational lens. Background galaxies appear stretched into arcs and mirrored images, warped by the cluster's gravity. The amount of distortion depends on the total mass of the cluster, not just its visible stars and gas, but all mass present. And here's the mainstream anchor. For decades, astronomers have known that visible matter alone cannot account for the observed gravitational effects in galaxies and clusters. Rotation curves of spiral galaxies, first carefully measured in the 1970s by Vera Rubin and colleagues, show that stars orbit at speeds implying far more mass than what we can see. That unseen mass is called dark matter. Webb does not see dark matter directly. No telescope does. Dark matter does not emit, absorb, or reflect light in any detectable way. Its presence is inferred from gravity, but Webb's ability to detect very early galaxies and map their distribution feeds directly into dark matter models. According to the standard cosmological model, lambda CDM, cold dark matter clumps together under gravity, forming halos that act as gravitational wells. Ordinary matter falls into these halos, cooling and forming stars and galaxies. The timeline and abundance of early galaxies therefore depend heavily on how dark matter behaves. If Webb is observing more luminous galaxies earlier than predicted, it could suggest that dark matter halos formed and merged faster than some simulations anticipated. Or it could imply that baryonic physics, gas cooling, star formation efficiency, was more aggressive within those halos. Historians still argue whether dark matter consists of weakly interacting massive particles, WIMPs, axions, or some yet undetected entity. Despite decades of experiments in underground detectors and particle accelerators, no direct detection has been confirmed. The case for dark matter remains gravitational. And here's where Webb subtly intensifies the conversation. By studying gravitational lensing in exquisite detail, Webb helps refine mass distributions within clusters. Strong lensing, where background galaxies appear as dramatic arcs, provides precise constraints on how mass is arranged. Comparing these observations with simulations tests our understanding of how dark matter clusters. You imagine space-time as a stretched sheet. Place a massive cluster on it, and the sheet dips. Light from background galaxies follows the curvature. Bending around the cluster, Webb captures the distorted images. From those distortions, astronomers reconstruct the invisible mass map. It's cosmic cartography using gravity as ink. Now consider early galaxies again. If some appear more massive than expected, perhaps their dark matter halos were denser or formed earlier. Alternatively, maybe our understanding of how gas converts into stars under early conditions needs revision. There's even a fringe but persistent idea. What if dark matter behaves slightly differently on small scales than lambda CDM predicts? Some alternative models propose warm dark matter, which would suppress small-scale structure formation compared to cold dark matter. Others explore self-interacting dark matter. So far, lambda CDM remains remarkably successful at explaining large-scale structure, the cosmic web of filaments and voids mapped by galaxy surveys. But small-scale discrepancies have been debated for years, including the so-called missing satellites problem and cusp core problem in dwarf galaxies. Webb's observations of early faint galaxies could add new data to those discussions. Historians still argue whether small tensions between theory and observation signal cracks in the model or simply reflect incomplete modeling of complex astrophysical processes. Science often advances by resolving such tensions without discarding the entire framework. You drift through a mental image of the cosmic web, vast filaments of dark matter stretching across hundreds of millions of light years, with galaxies forming at their intersections. Webb's deep fields are like tiny drill holes into that web, revealing its structure at earlier times than ever before. If the web appears more developed than predicted at a given epoch, the timeline of structure growth may need adjustment. But caution remains. Early mass estimates are sensitive to assumptions about stellar populations and dust. Lensing models rely on precise reconstructions. The cosmological parameters, like the Hubble constant, are measured with independent methods. Interestingly, there is already a tension in cosmology regarding the Hubble constant. Measurements from the early universe, via the cosmic microwave background, differ slightly from measurements of nearby supernovae. Historians still argue whether that Hubble tension signals new physics or unresolved systematic errors. Webb may contribute indirectly to that debate by refining distance measurements and galaxy evolution models. You pause with a soft realization. Looking deeper has not revealed a dramatic overthrow of dark matter theory. It has not replaced lambda CDM with something radically new, but it has sharpened the edges of existing questions. Are early galaxies too numerous? Are some too massive? Do lensing maps match predictions precisely? Each answer refines the role dark matter plays in shaping the cosmos. You hover beside the telescope, golden mirror steady, instruments humming in silence. Webb cannot see dark matter directly, but by mapping its gravitational influence, With unprecedented sensitivity, and by observing structure at earlier cosmic times, it helps test the invisible scaffolding of the universe. And that's the quiet power of looking deeper. Not to demolish foundations overnight, but to probe them, press gently at their edges, until you know whether they are as solid as you think. Dark matter remains unseen, but its fingerprints are everywhere, and Webb is reading them more carefully than ever before. Now you turn your attention to the stars themselves, not the galaxies they inhabit, not the black holes that anchor them, but the very first generation of stars that ever ignited. Because if Webb has pushed us closer to cosmic dawn than ever before, then one question hovers in the infrared glow. Did the first stars behave differently from anything we see today? You float beside the telescope as it collects faint spectra from galaxies only a few 100 million years after the Big Bang. These galaxies are not resolved into individual stars, too distant, too compact, but their collective light carries clues. The first stars, known as population 3 stars, are thought to have formed from primordial gas composed almost entirely of hydrogen and helium. No carbon, no oxygen, no iron. Those heavier elements did not yet exist. A mainstream theoretical prediction anchors this. Without metals to help cool collapsing gas clouds efficiently, the first stars were likely much more massive than typical stars today. Simulations suggest many may have ranged from tens to hundreds of times the mass of the Sun. Massive stars burn hotter and brighter and live much shorter lives. Instead of billions of years like our Sun, they may have survived only a few million years before exploding as supernovae or collapsing directly into black holes. You imagine one of these primordial giants igniting in total darkness. No previous starlight had illuminated the universe. No complex molecules drifted through space, just hydrogen clouds and gravity. And then fusion, a blaze of ultraviolet radiation piercing the cosmic night. If these stars were as massive as predicted, their deaths would have been extraordinary. Some may have ended in pair instability supernovae, cataclysmic explosions that completely disrupted the star, leaving no remnant behind. Others may have collapsed directly into black holes, seeding the early universe with heavy gravitational anchors. Historians still argue whether population 3 stars were exclusively extremely massive, or whether fragmentation in primordial gas clouds allowed for smaller stars as well. If smaller population 3 stars formed, some might, in theory, still exist today, extremely old and metal poor. Astronomers search for such relic stars in the halo of our Milky Way. So far, none have been found that are completely metal-free. Webb cannot directly image individual population 3 stars. They are too distant and too faint as single objects. But it can search for indirect evidence, galaxies whose spectra show extremely low metallicity, hinting at a dominant contribution from first-generation stars. You examine a distant galaxy's spectral lines. Oxygen is present, but perhaps in very low abundance. That suggests at least one previous generation of stars has already enriched the gas. The pure primordial phase may have been brief. That's the subtle implication. The first stars may have lived fast and died young, rapidly transforming their environments. A quirky but intriguing possibility. Some theoretical models suggest that primordial stars may have formed in binary systems, potentially leading to early gamma-ray bursts when one collapsed. If such bursts occurred, they could have injected enormous energy into surrounding gas, influencing early galaxy formation. Webb's data might eventually hint at such energetic events indirectly through chemical signatures. You feel the narrative shifting again. The early universe may not have been dominated for long by pristine, metal-free gas. Instead, enrichment could have happened rapidly, cascading from one generation of stars to the next. Historians still argue whether the transition from population 3 to population 2 stars, those with some metal content, was gradual or abrupt. The answer affects how we model early star formation rates and the pace of chemical evolution. Webb's observations of extremely distant galaxies help constrain that transition. If galaxies at redshift 12 already show measurable metal lines, then the first supernovae must have occurred even earlier. That pushes the timeline of stellar ignition closer to the Big Bang itself. You picture a cosmic sunrise not as a gentle glow, but as a sudden flare of massive stars igniting across dark matter halos. Short-lived, brilliant, transformative. And here's the philosophical shift. If the first stars were radically different from stars today, more massive, hotter, more explosive, then the earliest chapters of cosmic history were shaped by a stellar population unlike anything currently visible. The universe began with a generation of giants. You drift back slightly, letting the weight of that settle. Webb has not yet definitively identified a pure population 3 star, but it has narrowed the window. It has revealed galaxies so early that they likely contain echoes of those first stellar titans. It has shown that metal enrichment was underway surprisingly quickly. Looking deeper did not just extend the galaxy timeline. It pressed against the boundary where stars first appeared. And that boundary may be closer to the beginning than we once imagined. The darkness after recombination may have been shorter-lived. The cosmic dawn may have broken swiftly, dramatically. You hover in the quiet shadow of the sun shield, thinking about those first stars. Massive, brilliant, brief. They lived fast. They died young. And in doing so, they seeded the universe with the ingredients for everything that followed. Galaxies, planets, atmospheres, perhaps even life. Webb has not yet shown you their faces, but it has illuminated their legacy. And that legacy suggests the early universe was not timid. It was incandescent. Now you let your eyes wander across Webb's images again. Not the faint red dots at impossible distances, not the spectra with their tidy absorption lines, but the shapes, the silhouettes of galaxies themselves. Because something else is quietly unsettling in these deep fields. They look messy. You hover beside the telescope as another high redshift galaxy resolves into view. It's not a graceful spiral with well-defined arms like the Milky Way. It's not a smooth elliptical glow. It's clumpy, irregular, almost chaotic. A mainstream fact anchors this observation. In the nearby universe, galaxies generally fall into recognizable categories: spirals, ellipticals, lenticulars, classified originally by Edwin Hubble in the 1920s in what became known as the Hubble sequence. This tuning fork diagram organized galaxies by morphology and implied a loose evolutionary path. But when Webb peers back billions of years, that tidy classification scheme begins to fray. Early galaxies often appear as compact, bright knots embedded in diffuse halos. Some show elongated structures that don't quite resemble mature disks. Others look like multiple small clumps in the process of merging, and that makes sense. In the early universe, galaxy mergers were more frequent. Dark matter halos were assembling rapidly, pulling smaller systems together. Gas-rich collisions triggered bursts of star formation. Stability was rare. Historians still argue whether spiral structure requires a long period of relative calm to develop, or whether disk galaxies can form surprisingly quickly under the right angular momentum conditions. Webb's images suggest that while some disk-like structures may appear earlier than expected, many early galaxies are indeed turbulent environments. You imagine two young galaxies colliding, gas clouds compressing, star formation igniting in brilliant clusters, tidal tails stretching outward like cosmic taffy. These interactions are not rare accidents. They are fundamental to galaxy growth. A quirky but true detail: some early galaxies observed by Webb appear surprisingly compact yet extremely bright, sometimes nicknamed little red dots in informal discussions. These compact objects may host active galactic nuclei or intense starbursts. Their precise nature is still being debated. The diversity is striking. Instead of a smooth progression from small, faint blobs to orderly spirals, the early universe appears more like a workshop in motion, structures forming, merging, reshaping. You drift mentally across billions of years. Over time, repeated mergers can transform chaotic systems into more stable configurations. Angular momentum redistributes. Gas settles into rotating disks. Spiral arms emerge. Bulges grow. The tidy forms we see nearby are the result of long gravitational negotiations. But Webb shows you the negotiation in progress. Historians still argue whether the classical Hubble sequence represents an evolutionary path or merely a descriptive classification. Are ellipticals the end products of spiral mergers? Do spirals inevitably become ellipticals? Or do environment and initial conditions matter more than simple progression? Webb's early observations add texture to that debate. They suggest that morphological diversity existed very early. Not all galaxies followed the same path. You zoom in on a lensed galaxy magnified by a foreground cluster. Its light is stretched into a thin arc, but within that arc you can discern bright clumps, regions of intense star formation. These clumps may be the building blocks of larger structures. There's something almost biological about it. Cells clustering to form tissue, tissue organizing into organs. Except here the scale is measured in thousands of light years. And yet, despite the apparent chaos, the underlying physics remains simple. Gravity pulls matter together. Gas cools, stars ignite, mergers redistribute mass. Looking deeper does not reveal disorder without rules. It reveals complexity emerging from consistent laws. A mainstream anchor steadies you. Simulations of galaxy formation within the Lambda CDM framework already predicted a clumpy, merger-driven early universe. Webb is not overturning that expectation, but it is providing sharper, more detailed snapshots, allowing astronomers to test those simulations with unprecedented precision. Some structures appear more developed than anticipated at certain epochs. Others align beautifully with predictions. The picture is nuanced, not revolutionary, but richly detailed. Historians still argue whether the true revolution in astronomy comes from entirely new discoveries or from improved resolution that transforms vague hints into crisp realities. Webb belongs firmly in the latter category here. You hover in the cold quiet, letting the images flow past. Early galaxies are not polished masterpieces. They are drafts, sketches, rapid constructions in gravitational ink. And that realization changes how you picture cosmic history. The universe did not assemble its grand spirals in serene isolation. It built them through turbulence, collision, and relentless reshaping. Looking deeper has not made the cosmos neater. It has made it more alive, more dynamic, more visibly in motion. The tidy diagrams in textbooks remain useful, but they now sit beside Webb's chaotic portraits, reminding you that the real universe is rarely as symmetrical as its summaries. And perhaps that is the deeper shift. The farther back you look, the less finished everything appears. Not because the laws were different, but because the story was still unfolding. Now you let your gaze widen again, not just to individual galaxies or black holes, but to the space between them. Because if Webb is pushing us closer to cosmic dawn, then it is also illuminating one of the most mysterious transitions in cosmic history, the end of the Dark Ages. You hover beside the telescope as it collects faint light from galaxies formed within the first few 100 million years. Their ultraviolet radiation, now stretched into infrared, carries evidence of a dramatic phase change in the universe. After the Big Bang and the era of recombination, the universe was filled mostly with neutral hydrogen gas. Neutral hydrogen is excellent at absorbing ultraviolet light. That meant the early cosmos was, in a sense, foggy. Even as the first stars ignited, their high-energy radiation could not travel far without being absorbed. This period is often called the cosmic dark ages, not because there was no light at all, but because starlight could not propagate freely through space. Then something changed. As more stars and galaxies formed, their radiation began ionizing the surrounding hydrogen, stripping electrons from protons and transforming neutral gas into ionized plasma. Ionized hydrogen does not block ultraviolet light in the same way. Gradually, the fog lifted. The universe became transparent. This epoch is known as reionization. A mainstream fact grounds the timeline. Measurements of the cosmic microwave background, particularly from the Planck satellite, suggest that reionization was largely complete by about 1 billion years after the Big Bang. Observations of distant quasars also show that by redshift 6, the intergalactic medium was mostly ionized. But the detailed progression, how fast it occurred, which sources contributed most, remains an active area of research. Webb is now helping map that transition directly. By detecting galaxies at redshifts 10, 12, and beyond, Webb identifies the likely culprits responsible for reionization. The key question is whether early galaxies alone produced enough ultraviolet photons to ionize the universe, or whether additional sources, such as accreting black holes, played a significant role. You imagine a young galaxy blazing with star formation. Massive, short-lived stars emit torrents of ultraviolet radiation. That radiation escapes into intergalactic space, carving out ionized bubbles around the galaxy. As more galaxies ignite, these bubbles expand and eventually overlap, creating a fully ionized cosmos. Historians still argue whether the process was patchy and uneven ionized regions forming around clusters of galaxies before merging, or relatively uniform across space. Webb's ability to observe faint galaxies in different regions helps constrain that patchiness. You drift through a mental map of the early universe. Pockets of light pushing back against a sea of neutral hydrogen. The transition not as a single moment, but as a gradual brightening, like dawn spreading across a landscape. A quirky but fascinating detail. Astronomers study the Lyman alpha emission line of hydrogen to probe reionization. In a neutral universe, Lyman alpha photons are easily scattered and absorbed. If Webb detects strong Lyman alpha signals from very distant galaxies, it suggests that at least locally, the surrounding medium was already ionized. The presence or absence of that line becomes a diagnostic tool for cosmic transparency. Webb's observations are beginning to refine those measurements. Some distant galaxies show signs that they exist in partially ionized environments, hinting at the complex, evolving topology of reionization. you feel the scale of it again. The universe underwent a phase change on the largest possible scale. Not water freezing into ice, but hydrogen shifting from neutral to ionized across billions of light years. And it happened because stars turned on. Looking deeper has brought you closer to that turning point than ever before. Historians still argue whether reionization marks the true end of the universe's infancy or merely a milestone in a longer adolescence. But symbolically, it represents the moment when light gained dominance over darkness. You hover beside Webb as it quietly measures faint flux variations from galaxies at the edge of visibility. It does not witness the fog lifting in real time. It reconstructs it from ancient photons. Each high redshift galaxy is like a candle in that early mist. By counting them, measuring their brightness, and estimating their ultraviolet output, astronomers calculate whether they collectively could have powered reionization. Early results suggest that small, faint galaxies, far more numerous than bright ones, may have played a crucial role. That means the universe's transformation may have depended not only on spectacular quasars, but on countless modest star-forming systems working together. There's something quietly democratic about that. Not a single beacon, but a multitude of flickers gradually illuminating the cosmos. Looking deeper did not just reveal more ancient objects. It revealed the mechanism by which the universe became transparent. You imagine the final stages of reionization, ionized bubbles merging, ultraviolet light traveling freely across vast distances for the first time. After that, the universe would remain largely transparent, allowing galaxies to be visible across billions of light years, allowing you, billions of years later, to see them. Without reionization, much of cosmic history would remain obscured. Webb is not merely observing ancient galaxies. It is witnessing the epoch when the universe switched the lights fully on. And in doing so, it connects the faintest red smudges in its deep fields to one of the most profound transitions in cosmic history. Darkness did not vanish instantly. It retreated gradually, photon by photon, and Webb is tracing that retreat in exquisite infrared detail. Now you step back from individual discoveries, early galaxies, rapid black hole growth, reionization, and feel a deeper tension humming beneath it all. Because when enough small surprises accumulate, a larger question begins to surface. Are our models fundamentally wrong? You hover beside Webb as it continues its silent orbit around L2, mirrors aligned, instruments cold. It does not know that its data is being fed into cosmological simulations across Earth. It does not know that parameters are being tweaked, that researchers are debating whether lambda CDM, the standard model of cosmology, needs adjustment. But you know, the lambda CDM model has been spectacularly successful. It explains the large-scale structure of the universe, the cosmic microwave background fluctuations, the abundance of light elements like helium and deuterium formed in Big Bang nucleosynthesis. It predicts a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Those numbers are not guesses. They are derived from precise measurements, particularly from missions like Planck. And yet, Webb's early galaxy observations suggest that structure may have emerged faster than some simulations predicted. The Hubble constant, measuring the universe's expansion rate, shows a persistent tension between early universe and late universe measurements. Black holes appear massive very early. None of these individually overthrow the model, but together they create friction. Historians still argue whether such friction signals the beginning of a paradigm shift or simply the normal process of refinement. Scientific revolutions rarely announce themselves in advance. They whisper first. You imagine cosmologists staring at simulation outputs. Adjust star formation efficiency, modify feedback strength, tweak initial conditions slightly within observational uncertainties. Many apparent discrepancies can be resolved without discarding the framework. And so far, that's largely what has happened. Early claims that galaxies were impossibly massive have been softened with better spectroscopic data. Revised mass estimates bring many objects closer to theoretical expectations. The standard model bends, but it does not break. Still, there are intriguing possibilities at the edges. What if dark matter behaves differently on small scales? What if early gas cooling was more efficient due to processes not fully captured in simulations? What if there are subtle properties of dark energy that influence structure formation earlier than expected? These are not wild speculations. They are constrained hypotheses tested against data. A quirky but telling detail, cosmological simulations now require enormous computational resources, supercomputers modeling billions of particles to recreate cosmic structure. As observational data improves, simulations must increase in resolution and complexity. Sometimes discrepancies arise not because the universe is wrong, but because our computational approximations were incomplete. You drift mentally through a simulation box representing a patch of the early universe. Dark matter particles cluster into filaments, gas falls in, stars form, black holes ignite. Compare that virtual universe with Webb's deep field. The closer they match, the stronger the model stands. Historians still argue whether cosmology is entering a precision era where tiny deviations matter profoundly, or whether the broad strokes are already secure and only fine details remain to be filled. Webb pushes us firmly into that precision regime. You feel the weight of that transition. For most of human history, cosmology was philosophical. Then it became observational. Now it is quantitative to astonishing accuracy. A few percent difference in predicted galaxy abundance at redshift 12 can spark serious discussion. Looking deeper has not shattered cosmology. It has stress-tested it. And so far the structure holds, though with some interesting creaks and flexes. You glance toward the cosmic microwave background again in your mind, the faint afterglow measured at microwave wavelengths, mapping fluctuations from when the universe was 380,000 years old. That map fits beautifully with Lambda CDM predictions. Any radical change to the model must still preserve that success. This is why cosmologists are cautious. You cannot casually discard a framework that explains so much so well, but you also cannot ignore persistent tensions. The Hubble tension remains unresolved. Early galaxy formation may require refined modeling. Black hole seeds demand explanation. Historians still argue whether we are on the brink of discovering new physics, perhaps related to dark matter interactions or evolving dark energy, or whether improved data will gradually reconcile everything within the existing model. Webb is not issuing proclamations. It is supplying evidence. And that evidence suggests something subtle but profound. The universe may be slightly more efficient, slightly more dynamic in its early stages than our first approximations assumed. Not chaotic beyond comprehension, not in need of complete reinvention, but richer, more textured. You hover beside the telescope as it slews toward yet another faint target. It continues collecting photons from epochs we once thought unreachable. Looking deeper has not changed the laws of physics, but it has reminded you that laws expressed in equations still require precise calibration against reality. The universe is not obligated to match our simulations perfectly. It is only obligated to obey its own rules. And with every new data set, Webb is helping you determine whether the rules you've written down truly capture the cosmos as it is, or whether a subtle revision awaits in the margins. For now, the model stands, but it stands under brighter light than ever before. Now imagine someone, a century from now, looking back at this moment in astronomy, not at the launch footage, not at the early press releases, but at the quiet accumulation of data points that slowly reshaped how humanity understood its cosmic story. You float beside Webb, and for a moment you step outside the present. Future historians of science are writing about the early 21st century. They describe it as the era when the observable universe became sharply resolved, when vague smudges turned into structured galaxies, when speculative atmospheres became measured spectra. A mainstream parallel anchors this perspective. In 1609, when Galileo first turned a telescope toward the sky and saw the moons of Jupiter, it did not immediately overturn every worldview. But it initiated a cascade of refinement that eventually displaced Earth from the center of the cosmos. At the time, it was just an instrument revealing unexpected detail. In hindsight, it was transformative. Webb may occupy a similar place in future narratives. Historians still argue whether transformative scientific eras are recognized in real time or only appreciated fully in retrospect. Living through one often feels less dramatic than textbooks later suggest. There are no orchestral swells, just incremental updates to datasets and models. You imagine a future student scrolling through archived Webb deep fields. What seems extraordinary to you, galaxies at redshift 13, may feel foundational to them. They may take for granted that we can trace cosmic structure to within a few 100 million years of the Big Bang. That normalization is part of progress. But think about what shifted. Before Webb, the early universe was dimly constrained. We inferred its behavior largely from the cosmic microwave background and extrapolated forward using models. After Webb, we began observing galaxies directly in that early epoch with unprecedented clarity. Before Webb, exoplanet atmospheres were detected but sparsely characterized. After Webb, comparative atmospheric chemistry became routine. Before Webb, the epoch of reionization was mapped indirectly. After Webb, candidate galaxies contributing to it could be studied individually. These are not small adjustments. They represent a tightening of the cosmic narrative. You hover beside the telescope as it quietly transmits data back to Earth. There's no fanfare in the vacuum. No applause, just photons turned into numbers. A quirky but revealing detail, Webb's data becomes public after a proprietary period, allowing scientists worldwide, not just the original observing teams, to analyze it. That democratization of data means discoveries often emerge from unexpected quarters. Some early high redshift galaxy candidates were identified by independent researchers combing through released images. Science at this scale becomes collaborative and cumulative. Historians still argue whether the 20th century belonged to theoretical breakthroughs, relativity, quantum mechanics, while the 21st century may increasingly belong to precision observational refinement. Webb sits at that intersection, guided by theory, testing it with exquisite detail. You consider how our cosmic self-image has evolved. Once we thought the Milky Way was the entire universe. Then we learned it was one galaxy among billions. Then we discovered planets orbiting other stars. Now we are measuring the atmospheres of those planets and observing galaxies near cosmic dawn. Each step has decentered humanity slightly more, while simultaneously expanding the scope of what we can know. Looking deeper did not make the universe smaller or simpler. It made it more expansive and intricate. Future historians may write that Webb marked the moment when cosmic infancy stopped being theoretical abstraction and became observational territory. When the early universe shifted from equations on chalkboards to spectra on screens, you drift in the silent shadow of the sun shield, thinking about how fragile that perspective shift is. It depends on delicate mirrors aligned to nanometers, on cryogenic instruments cooled to extreme temperatures, on decades of engineering decisions, and yet from that fragility emerges clarity. Historians still argue whether technological leaps drive conceptual revolutions or whether new ideas demand new tools. In truth, they feed each other. Without infrared sensitivity and a large segmented mirror, the early universe would remain partially hidden. Without theoretical models predicting what to look for, the data would lack context. Webb stands at that crossroads. Looking deeper has not rewritten every page of cosmology, but it has annotated them, added footnotes, corrected margins, highlighted sections in brighter ink. And perhaps that is how revolutions truly unfold, not as explosions, but as sharpenings. You imagine that future student again, reading about the Webb era. For them, early galaxies at redshift 12 may be as familiar as the Andromeda galaxy is to you. They may laugh gently at how astonished we were. But that astonishment is part of discovery. You hover one last moment in this imagined future past. The golden mirror continues reflecting ancient light. The data archives grow, the models refine, and history quietly records that this was the time when humanity looked deeper than ever before and found a universe slightly more ambitious, slightly more dynamic, and slightly more complex than expected. And yet, for all that Webb has revealed, you begin to sense its edges, the boundaries of what even this extraordinary machine cannot see. You float beside the telescope at L2, its sunshield stretched wide, its mirrors steady and cold. It feels omnipotent in the dark, but it isn't. No instrument is. Webb observes primarily in the near and mid-infrared range, roughly from 0.6 to 28 microns. That makes it exquisitely sensitive to red-shifted starlight, warm dust, and molecular signatures. But it does not see X-rays. It does not see radio waves. It cannot directly observe the cosmic microwave background in the way Planck did. A mainstream fact anchors this limitation. Astronomy works best when multiple wavelengths are combined. X-ray telescopes reveal high-energy phenomena like hot gas in galaxy clusters and black hole accretion disks. Radio rays map cold hydrogen gas and the large-scale structure of the cosmic web. Webb is powerful, but it is one piece of a larger observational ecosystem. You imagine trying to understand a symphony by listening only to violins. Beautiful, yes. Complete, no. Webb also cannot see beyond a certain cosmic horizon. Even though it observes galaxies from within a few 100 million years of the Big Bang, it cannot peer past the surface of last scattering, the epoch that produced the cosmic microwave background. Before about 380,000 years after the Big Bang, the universe was opaque plasma. Photons scattered constantly off free electrons. No telescope using electromagnetic radiation can see through that wall. To probe earlier still, scientists rely on indirect evidence, gravitational waves, particle physics experiments, theoretical models of inflation. Historians still argue whether we will ever directly observe evidence of cosmic inflation, the rapid expansion hypothesized to have occurred fractions of a second after the Big Bang, or whether it will remain an elegant but indirectly supported theory. Webb does not settle that question. There are also practical limits. Even with its large mirror, Webb can only detect galaxies down to a certain brightness. The faintest, smallest systems at extreme redshifts may remain below its sensitivity threshold. There may be countless dim galaxies contributing to reionization that Webb can barely detect, if at all. You imagine them tiny, flickering systems too faint for even this golden eye. Their existence inferred statistically rather than imaged directly. Then there's spatial resolution. While Webb's mirror is larger than Hubble's, at extreme distances even it cannot resolve fine internal structure. Distant galaxies remain compact smudges, their internal dynamics inferred from spectra rather than crisp images. A quirky but revealing constraint. Webb must keep its sun shield oriented toward the sun at all times. That means it cannot point everywhere in the sky whenever it wants. Its field of regard is limited by thermal requirements. The telescope's cold side must remain in shadow. Even ambition must obey thermodynamics. And then there's time. Webb's mission lifetime is finite. It carries a limited amount of fuel for station keeping at L2. Current estimates suggest it could operate for 20 years or more, thanks to a highly efficient launch, but not indefinitely. At some point, it will drift, its instruments falling silent. Historians still argue whether future space telescopes, like the proposed Habitable Worlds Observatory, will surpass Webb in size and sensitivity, particularly for detecting biosignatures in Earth-like exoplanets. Webb is a beginning, not an endpoint. You feel the humility in that. Looking deeper has changed your understanding, but it has not revealed everything. Dark matter remains unseen directly. Dark energy, responsible for the accelerated expansion of the universe, remains mysterious. The nature of inflation is uncertain. The ultimate fate of the universe, heat death, big rip, something else, remains theoretical. Webb sharpens the questions. It does not eliminate them, and perhaps that is the most honest outcome. You drift beside the telescope and consider the possibility that the universe may always recede just beyond the reach of your instruments. As technology improves, horizons expand, but new mysteries appear. A mainstream reflection grounds you. Every major advance in observational astronomy has revealed unexpected complexity. When Galileo saw Jupiter's moons, he did not solve planetary formation. When Hubble revealed galaxies beyond the Milky Way, it did not resolve dark matter. Each new window multiplies questions. Webb is no exception. It has revealed early galaxies but raised questions about their rapid growth. It has measured exoplanet atmospheres, but not yet found definitive biosignatures. It has refined reionization timelines, but not fully mapped the faintest contributors. Looking deeper has illuminated the universe, but not exhausted it. You feel the quiet comfort in that incompleteness. If Webb had answered every question, the story would end too neatly. Instead, it has done what great instruments always do. It has expanded the frontier. You hover in the stillness at L2. The sun glows on one side of the shield. On the other, the mirrors drink in ancient light. Beyond Webb's reach lie earlier moments. Fainter galaxies, subtler signatures, but within its reach, an extraordinary transformation has occurred. The unknown has not vanished. It has become sharper. And that sharpening, paradoxically, makes the universe feel larger than ever. Now you begin to sense the next step forming, not in the data already gathered, but in the questions that data has sharpened. Because whenever a telescope like Webb expands the observable frontier, it doesn't close a chapter. It outlines the next mission. You float beside Webb at L2 and imagine the planning rooms back on Earth. Scientists are already drafting proposals for observatories that will build directly on what Webb has uncovered. A mainstream example anchors this future. NASA is developing concepts for the Habitable Worlds Observatory, a next-generation space telescope designed specifically to image Earth-like exoplanets around sun-like stars and search for biosignatures directly. Unlike Webb, which primarily studies transiting planets, such a telescope would use advanced coronagraphs or star shades to block starlight and isolate the faint glow of orbiting rocky worlds. That is a direct response to Webb's atmospheric successes. Webb proved we can measure exoplanet chemistry. The next step is detecting oxygen, ozone, methane combinations on truly Earth-sized planets in habitable zones. You imagine a future telescope with a mirror even larger than Webb's, floating perhaps at L2 as well, its optics tuned not only for infrared, but for visible light where oxygen signatures are strong. It would build on Webb's foundation, just as Webb built on Hubble's. Historians still argue whether technological progress in astronomy follows predictable generational leaps, roughly every 20 to 30 years, or whether funding cycles and political priorities create uneven bursts of advancement. Webb itself endured decades of delay before launch. Its successors will likely face similar challenges, but the scientific direction is clearer now. Webb's early galaxy discoveries highlight the need for even deeper surveys and higher resolution at extreme redshifts. That motivates future infrared observatories and massive ground-based telescopes like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, which will complement Webb with adaptive optics and enormous light-collecting power. You drift mentally to Earth's mountaintops, where these giant mirrors will soon peer into the sky. Combined with Webb's space-based clarity, they will refine measurements of early galaxy structure, black hole growth, and chemical enrichment. Then there's gravitational wave astronomy. LIGO has already detected black hole and neutron star mergers. Future space-based detectors like LISA will measure gravitational waves from supermassive black hole mergers, events likely common in the early universe Webb is observing. That will connect infrared light to space-time ripples directly. A quirky but thrilling thought. One day we may observe a high redshift galaxy with Webb's successor and simultaneously detect gravitational waves from merging black holes within it. Multi-messenger cosmology across billions of years. Looking deeper has not just changed what we know, it has clarified what we need next. Webb's data also feeds into particle physics. If dark matter behavior must be constrained more tightly to match early galaxy formation, that informs laboratory searches on Earth. Underground detectors may refine their sensitivity based on cosmological parameters derived from telescopes. Historians still argue whether astronomy and particle physics will converge more tightly in the coming decades, perhaps revealing the true nature of dark matter or dark energy through combined evidence. Webb strengthens that bridge. You glance again at the golden mirror. It feels almost modest now, though it is anything but. It has shown that early structure formed rapidly. It has mapped chemical fingerprints across cosmic time. It has analyzed alien atmospheres. And in doing so, it has made the next questions unavoidable. How early did the first stars truly ignite? How common are Earth-like atmospheres? What is dark matter? What is dark energy? Each question now feels sharper, less abstract. There's a mainstream pattern in science. When observational capability expands, theory must keep pace. Webb has forced cosmological simulations to increase resolution and sophistication. It has required atmospheric models for exoplanets to become more nuanced. It has demanded better calibration of stellar population synthesis codes. It has raised the bar. You imagine future astronomers looking back and seeing Webb as the hinge between eras. Before it, early galaxies were largely speculative beyond certain limits. After it, they became directly observable. Before it, exoplanet atmospheres were tentative glimpses. After it, they became rich data sets. Looking deeper did not finish the story. It outlined the sequel. You hover in the cold quiet, feeling both satisfaction and anticipation. The universe did not change when Webb looked at it, but our roadmap did. And perhaps that is the deeper meaning of changes everything. Not that physics collapsed, not that cosmology was overturned, but that the path forward became clearer. The unknown is now better defined, and that definition is what drives exploration. Webb continues to observe, night after night, though night and day have little meaning at L2. Each exposure adds another pixel to humanity's cosmic understanding. Behind every pixel lies a question. Ahead of every question lies another instrument waiting to be built. Now, at the edge of everything Webb has shown you, you let the view widen one last time. Not just to galaxies or atmospheres or dark matter halos, but to your own perspective. You hover beside the telescope at L2, 1.5 million kilometers from Earth. The blue planet is small from here, half-lit, drifting against blackness. On the other side of the vast sun shield, ancient photons continue to fall, each one carrying a story billions of years old. James Webb looked deeper than ever before. And what it found did not shatter the universe. It expanded it. Early galaxies formed faster than expected. Not impossibly fast, but briskly enough to make cosmologists recheck their equations. Black holes grew in the cosmic dawn. Heavy elements appeared quickly, seeding future generations of stars and planets. The fog of reionization lifted through the collective effort of countless young galaxies. And closer to home, if 40 light-years can be called close, alien atmospheres revealed water, methane, carbon dioxide. chemistry rich enough to invite serious questions about life beyond Earth. A mainstream truth anchors everything you've seen. The universe is about 13.8 billion years old, expanding, structured by dark matter, accelerated by dark energy. Webb has not rewritten those fundamentals, but it has refined them, sharpened their edges, filled in their earliest chapters with color instead of silhouette. Historians still argue whether the phrase changes everything is ever literally true in science. Usually, knowledge evolves by accumulation, not explosion. And yet, sometimes accumulation reaches a tipping point. Sometimes the picture becomes clear enough that the world feels different, even if the equations remain intact. You think about what has shifted before Webb. The first few 100 million years after the Big Bang were mostly theoretical terrain. Now they are observational territory. Before Webb, exoplanet atmospheres were faint hints. Now they are measurable chemical environments. Before Webb, the early growth of structure was modeled primarily from simulations. Now it is constrained by direct infrared evidence. The universe feels older and younger at the same time. Older because you can see so far back. Younger because its early chapters seem more energetic, more dynamic, more alive than expected. A quirky but grounding thought slips in. Every photon Webb captures began its journey long before humans existed, long before Earth had oxygen-rich air, long before multicellular life. And yet those photons end their journey on mirrors engineered by primates who learned to polish gold to nanometer precision. That continuity is staggering. You float in silence and consider scale. The observable universe contains perhaps hundreds of billions of galaxies. Each galaxy contains billions of stars. Many stars host planets. Webb has sampled only tiny patches of sky, grains of sand held at arm's length, and already found thousands of galaxies within them. Looking deeper did not make the universe smaller. It made it denser, more populated, more chemically evolved, earlier than expected. And in that density, your place shifts subtly. Not diminished but contextualized. You are part of a species that built a machine capable of reading infrared barcodes from galaxies formed near cosmic dawn. A species that can infer the presence of water vapor in the atmosphere of a planet orbiting another star. That changes something not about the universe but about you. Historians still argue whether humanity's cosmic perspective evolves in sudden leaps or gradual acclimations. When Copernicus displaced Earth from the center, when Hubble revealed other galaxies, when exoplanets were discovered, each shift expanded the horizon of belonging. Webb continues that expansion. The universe is not static and slow. It is efficient, dynamic, capable of assembling structure quickly from almost nothing. And it is transparent enough now, thanks to reionization billions of years ago and engineering brilliance today, for you to witness it. You take one last imagined look at Webb's golden mirror. It tilts slightly, locking onto another faint target. Another deep field, another spectrum. The work continues. Looking deeper did not end the mystery. It clarified it. The cosmos remains vast. Dark matter remains unseen. Dark energy remains enigmatic. Life beyond Earth remains unconfirmed. But the boundaries of ignorance have receded, and that quiet retreat of darkness, photon by photon, dataset by dataset, is what truly changes everything. You let the image soften. Earth glows blue behind the sunshield. The mirror gleams faintly. Ancient light keeps arriving. The universe has always been there. Now you are simply seeing it more clearly than ever before.